All right. So, yeah, so the focus of this talk is to talk about method confirmation and method calls in general. So, um, let's see, let me make a new text file here. I won't share in a HackMD, it's just too hard. So yeah, Rust obviously has methods, and specifically because Rust is special, it has basically, when you write code, looks like, you know, call, basically unlike other programming languages, the steps that Rust has to take to actually find out what method that we call here is complicated both by the fact that impl blocks can be implemented for kind of a creative set of types. You can write, impl, as except for, I guess, considering coherence and orphan rules and things like that, you can write basically any type for an impl block, and you can impl a trait for, any type. And that's very different than, the way that like Java does it, where the methods that you're able to call in a type are like paired with the definition of the type. So when you implement a class, you say what not super traits, but like the interfaces and the super classes of the classes in Java, for example. And so whenever you have an instance of that class and you do the dot operator and you're looking for the method, it's very easy to find out what methods to call in that class because they're right there. The compiler doesn't need to do that much except for possibly looking at super classes and super, like interfaces with default implementations of methods to find basically what the things that you need to call on them are. So the way that Rust does it is pretty involved. It's split into a few different steps, and this happens a lot in Rust, where it's split into kind of into two pieces. So this happens for method probing, or this happens for method selection. This also happens for trait selection, where we split into two parts, where one's kind of like a test out and find all the things that we might want to consider. It's called a probe. And then the other half of that is once we actually like take the list of things that we're considering, the methods that we could possibly call, not considering any preference over we should prefer calling these methods first over these methods, but just assembling all the different options that we have. Once we have that, we need to take that set and apply rules like inherent methods have preference over trait methods, and in-scope traits can only be called, and out-of-scope traits can't be called until we have a single unambiguous method that we know that we're going to be calling. And once we have that, then we basically redo the steps to make sure that the method is being called on the right types, and that all the type inference machinery is inferring all that we know about the method. So that's kind of abstract. I will also, let me make sure I can pull up the chats in case anyone has a question. Where is the chat? Clicking the chat button, it's not showing anything. That's great. Anyways, whatever. If anyone has any questions, unmute yourself and say something really loud. But yeah, so this is a really abstract. I mean, I didn't really explain anything in this example code. I should have possibly put together a bunch of example code, but I think it's probably better just kind of walk through the steps and maybe talk about motivating examples when we get to the parts that are kind of interesting and special. So we start with kind of the entrance in type checking. So I guess let me step that basically one step behind. So in comparison to other kinds of, we don't know this information, let's resolve it, method calls are resolved during the type checking phase of Rust. So when we're trying to find out like an object or like a class, or not a class, a struct name in Rust, that happens during a step before type checking called resolution. But because methods can be because basically inference can affect, like what a method actually can dispatch to. Like in this case, this FMT function could be display FMT, this could be debug FMT, this could be an inherent method called FMT. And what that is depends on the type of this X expression. The left-hand side of the dot is what I'm going to be calling the receiver of this method. I don't know why it's called the receiver. Go calls it the receiver. I think C++ also calls it the receiver. But it depends on the type of this receiver, and we'll find out as we're walking through the method probe code that unlike name resolution, where if we want to know that this name string resolves to the string inside of std string or whatever, wherever it is, it's in the preludes, it didn't really matter. We don't have enough information during basically before type checking to do the same thing for method calls. We could write a language where method calls need to be unambiguous at the name resolution time, but that means that Rust would be a lot less powerful. So basically, when we're lowering from the AST and going through all the steps of taking the Rust code that we've written and putting it and turning it into the Rust code that we do type checking on, there is a oh cool. Yes, thanks.
Sorry,
Eric.
I was just commenting on what you
no, that's
said
really
about
cool context. I'll repeat it for the recording. But Eric said that early object-oriented languages like Smalltalk treated method calls as sending a message to an object. So the thing that is on the left-hand side of the dot, the thing that we're calling the method on is basically it's a receiver because it's receiving the message. In this case, X is receiving the message of FMT. Cool. Thanks for the context. But yes, as I was saying, as we're lowering from the AST, basically what we parse here into the representation of the Rust code that we do type checking on, we don't actually do that much for method calls. We basically represent it as the same thing. We represent it as there's a receiver, there's a name, this identifier here, FMT is stored basically just as an identifier, and then we have a list of arguments. So let's jump into the method call code because that's actually where it's interesting. I can show you. So it's check method. I think it's called check method call. Yes, here in, let me collapse this. So there's this function called check method call. It's called by, there's like a hierarchy of like other check functions. It starts with check expr, which checks all the expressions, and then based off types of the expression, we go into kind of more specific code. So if it's a method call, we end up calling check method call. This expr is the receiver of the method call, and segment is that's the path segment, which is basically just the identifier of the, never mind. So this expr, I lied, is the whole method call expression. The receiver is the receiver, as I said before. The segment is the thing after the dot and right before the args. So it's like dot fmt dot clone. And then here's the args. And we pass this thing called an expectation, which is basically just like hints. So if we know that, for example, if we have like let RCVRT is tie, then we pass this tie expectation back up to the check expr. And this helps us to do inferencing in cases where things are ambiguous. This helps us infer like the generic argument of a collect call and stuff like that. I don't know if the expectation actually participates in method calling. I don't think it actually does. Not that it really matters here, though. This is kind of type checking 201, not 101, for when we have kind of the interesting side effects of inference and stuff like that. Because expectations aren't just, they're not always specific values. They're not saying, I expect this expression to type check as a tie. There are other expectations like, I want it to be something that could be coerced to a tie. I want it to be something that can be unsized, etc. So the first thing we do when we're checking a method call is we check the expression of the receiver. So we recurse into the receiver, we type check it, and we return its type back. And as I said before, in this example code, the type of this receiver heavily influences what we do method call, like how we do the method call. So we basically need to unambiguously know what this receiver type is. And we assert that we unambiguously know what this type is by calling this function called structurally resolved type. And all that does is it basically tries to resolve all the inference variables inside the type, using all the obligations, all the traits that we know that it's obligated to implement. If it's a type variable, or if it's not a type variable, we just return it up because it's no longer ambiguous. If it is a type variable, then we would basically report an error saying that we expect to know what the type of this expression is at this point. I think all of y'all have probably seen that error somewhere in your Rust code. It's like not enough type information. So that's where this happens. And we return basically an error expression. This is basically like a type that we don't know anything about, but that it has more lax rules on. It can be unified with everything because we don't care what it is because we've already reported an error. So yeah, once we've structurally resolved the tie, we now have the receiver type with enough information to do something with it. And we go into the kind of the meat of the method call, and we call this method called lookup method. So lookup method performs method lookup, is basically takes all the same input things that we gave it, except for in a different order with a bit more stuff destructured. But basically it performs the looking for a method, assembling all the things that we could possibly call, choosing the best one and confirming it, and basically equating all the types and returning back this method callee, which is basically just the def ID of the thing that we're calling, the substitutions that we have on the method call, and the signature that we expect this method call to have. So I guess I might be a little bit verbose here because people might be watching this. They might have not touched the Rust compiler before, but a def ID just identifies every item in the like in Surface Rust, and substitutions are just basically generic parameters. So, and this is basically, and then also the signature that we've substituted these generic parameters in for, so we can check all the arguments, match all the arguments that we expect them to have, and we can check that the output expression is correct, and we can return it back to whoever called check method call. So this is in lookup method. Lookup method's broken into a few different parts. As I said before, we do the probe where we choose the best candidate for a method call, considering all the rules that we have for inherent methods have precedence over trait methods and other things like unstable methods behind feature gates are prioritized less than methods that are not behind feature gates, things like that. Within this function, there's a bunch of other things like linting and error reporting, but that doesn't really matter. So I will mostly be skipping over the parts that are kind of the tedium of having to maintain Rust that has grown since 2015, and instead jump into the interesting parts. So the first part that we go into is this operation called lookup probe. So what it does, again, is it really only, we don't consider the arguments when we're doing a method call. We only really consider this receiver tie. That's why we don't pass in this args here, but instead we just pass in the identifier of the method that we're calling, the self type. We pass in this call expert again. It's kind of redundant, but we just pass it in because we use it for things like the span of the error. And then we specifically, importantly, is we pass in this thing called a probe scope. So normally in normal Rust code, we only consider the traits that are in scope for the module. So for every module, we only consider the traits for a trait method call that are imported with a use statement. This is because we don't want to have some crate dependency change the number or the crates that we see from upstream in a way that would then like cause our code to no longer compile. So inside the lookup probe, we jump into this function called probe for name, which is basically just lookup probe with even more arguments. So we pass in this thing called isSuggestion. This is used to just basically suppress error messages when it isn't a suggestion, but we're on the good path. We're actually doing real type checking. So we don't consider this to be a suggestion. We actually want to report error messages. And we also want to set the probe mode to method call. So the probe mode is split between method call and path. We use the same logic to do method probing for like the universal function call syntax like t method, and also t dot method. And this is because even if we're not using the dot operator to do a method call, there's still some ambiguity in this expression. If we're calling t without a trait, then we still need to find out what trait is providing this method, and we have rules on which ones we prefer and things like that, in the same way that we have rules for assembling this pick for the method. So but they have different rules. They have different things that they consider. Dot method call only considers things with self receivers, whatever. So, and this obviously doesn't consider things that have self receivers. Dot method calls also participate in auto-deref and autoref, versus universal function call syntax does not participate in auto-deref or autoref. Let's jump back down into lookup probe for name, and probe for name is basically just the self-explanatory probing for a method with that name, and it does this thing called probe up. Probe up implements kind of the first big step of the method probe kind of process, and what it does is it basically assembles the ladder of auto-deref steps. So whenever you are calling a method on an expression, we want to know all the things that it auto-derefs to. So auto-deref is the process of repeatedly applying the deref trait to a type until we get to something that no longer implements the deref trait. And so, for example, the auto-deref for like this type, let me just put this in the comment because I don't want it to have weird highlighting. So box of t. So this would auto-deref from ampersand box of t to box of t, or a box of slice of t to t. So these are the auto-deref steps for like a reference to a box of a slice of t, except, and we can jump into this method. We actually consider a few more kind of special things, and I'll explain why. And I keep going back up to the top of this function because I keep jumping around. So we go down to probe for method, probe up. And as I said before, paths don't consider, I'm gonna give me a second here, kill Zulip. I keep hearing the Zulip sound. Path calls don't consider any auto-derefs. So all they do is they kind of assemble one candidate step, which is just the self tie that we got passed in. So every rung in this auto-deref ladder is associated with the candidate step with the self type, and path calls only have one self type that they consider. It's just the path that you put on the right hand or on the left hand side of the angle brackets. For method calls, we call this query called method auto-deref steps. We pass in the self type and we get basically this ladder of auto-deref steps back. The implementation of method auto-deref steps is right below it, though. It's a query because this is a possibly expensive operation. We want to cache it because we call methods on a bunch of different types. We don't want to have to do this over and over and over again. We can just do it once per type that can be cached in the query system. So what we do is we assemble this, we instantiate this thing called the auto-deref, which is an iterator that iterates basically through all these auto-deref steps. We include raw pointers, so we allow ourselves to auto-deref past like const pointers for, I think that's for self receivers, like arbitrary self receivers that look like impl foo. I might be wrong about this. You can write arbitrary self receivers, and we want to be able to, I think we want to be able to do auto deref on this. Anyways, I guess it didn't really matter. So we go through all these auto deref steps. It's an iterator again, so we just map basically every item in this iterator with this candidate step where we just kind of wrap that self type back up. We save some special information about it, like whether an unsize has been done, if the type that we reached in the auto deref step is a raw pointer, then we set reached raw pointer to be true, and that's where we, I guess, consider these include raw pointers to do unsafe derefs. And then we get to the bottom of the auto deref chain, and we do one more kind of special auto deref step where we, if we have an array type, we actually unsize it into a slice type of the same type. So if we go back to my example of this auto deref ladder, if I change this slightly, if we just consider the auto deref steps, it would look like this. We actually also consider T, the slice T, as the final step in the method probe if we are still looking for methods. And this is to allow things like us calling like 1, 2, 3, which has the type. This does not have a slice type. This has an array type of 3, like with a length 3. We're allowed to call slice methods on it, like .len. And this is just, I guess, because implementers of Rust at this point probably didn't want to have to duplicate all the methods on arrays, specifically because that was before we had const generics. So we weren't able to write like impl for every array type. Like can't write like impl, const n usize, no t. And so we get around that by basically assembling one more auto deref step where we go from an array to a slice.
So is that last auto deref step there, is that sort of like an unsizing coercion, or does that force an unsizing coercion?
What do you mean by force an unsizing coercion?
I guess just that since slices.
Oh, I guess yes, it does.
Okay.
So it records an unsize adjustment if we actually get to that point. That happens during the method confirmation. Yeah, that happens during method confirmation, and this is only for from arrays to slices. All other unsizing, like you can't, if you have an inherent method on a din trait, you can't call like some concrete implements trait dot method. Like that doesn't work. So, and this actually happens in the Rust compiler. We have a trait called astconv that has a bunch of inherent methods implemented on it. And in order to, there's a few things that implement astconv. One's called item context. So if you have an item context I, I item context, you can't call I dot inherent method on din astconv. You have to call it like din astconv, like inherent I, which sucks, but it's much harder to know all the different things you can unsize a concrete type into, all the din traits that you can unsize into, versus arrays. It's basically hard coded. We know the one thing that we want to unsize it to, which is a slice. So, and again, this is just kind of historical implementation detail to make method calls from arrays to slices work. And so it would require some really creative kind of, for its compatibility work to make this work for inherent methods on din. Even though we would want it to happen, it's just a much harder problem to solve. Something I've looked into and then said like, wait, this is way too hard. So yeah, so that is what happens in this assemble method auto deref steps. It basically just gives us a list of all the auto deref steps, including this kind of final slice to or array to slice unsize. If during this process we ever reach an inference variable, then we actually consider that to be an error. So if we were going down the rungs of the auto-deref ladder, and we have something like, that's the arc of underscore, we would auto-deref this into arc of underscore, and this would turn to underscore, and this would be an error because it's possibly ambiguous, because we may have some method implemented on this underscore type that we don't know yet. So we just consider that to be an error. We end up reporting a very similar error where we don't have enough information about the type that we're implementing. So yeah, or sorry, the type that we're calling method on. This happens here. So if there's a bad type, then we call structure result type on it, which will then cause that same error message that they said the needs more type information, cannot resolve what this is, specify it. But in the case that we don't, we don't hit an inference variable, we have assembled this steps, auto-deref steps result function. It's basically just a struct that has an array of these auto-deref steps, and we have some logic around recursion limits, and for suggesting features if we have ambiguities and things like that. But if that all worked, then we hop into something called a probe. So a probe on the inference context is basically just like, let's try doing some type inferencey things without having any side effects. And inside this probe, we construct this thing called a probe context, which basically has all the information that we're going to need throughout this method probing context, or method probing process, span, the mode, as I said before, is it a path or like a dot method call, the name, the return type, which I don't know if we actually use that for anything or if we just use it for error reporting. I think we just use it for error reporting, but we'll see. We'll find out. Pass in this orig values, which are the query values that all the inference variables and stuff like that we had when we called this query, the method auto-deref steps, and then the scope of the expression. So this is used to find the in scope traits and things like that. So we first start out by assembling inherent candidates. So inherent candidates are things that are not associated with a trait. There's a big asterisk with that because certain things are considered inherent candidates for special types, but we will see. And then depending on whether or not we're considering traits in scope or all traits, we either assemble extension candidates for traits in scope, which are basically we consider all the trait methods, or we do that, but instead of limiting to the traits in scope, we just consider all traits. This probe scope all traits mode is used for diagnostics. It's for things like you may have wanted to call this trait, but it wasn't imported here. So it doesn't really matter. It basically just does the same thing, except they filter out the traits that they consider differently. But let's jump into assemble inherent candidates. Let's see how that does. So for each step in this rung of this ladder of auto-deref steps, we want to call assemble probe on it. What that does is it just takes a self type out of that query response, the basic thing that we got from this method auto-deref steps query, and we match on the self type. So for most types, I guess I'm going to go out of order here, but let's start out with ADTs, which are structs, unions, and enums. We look at the impulse for that ADT, basically things where the self type of the impl can be like, it's obviously that ADT, and we consider all the methods on that have the same matching name. We have a lovely feature called Rustc has inherent impulse that allow us impl inherent methods on impls that are outside of the crate that like define the type. So we need to also assemble those as well. It happens very similarly. We basically just take the impl and make sure it matches the thing that we're trying to call first. So I won't jump into that one, but it may be useful to jump into this assemble inherent impl candidates for type. So all that does is it calls inherent impls for a def ID. The def ID is that the thing that we're actually considering. In this case, it's like the ADT. So we pass in the struct's def ID. We only consider one layer of the type onion. So if it's a struct of a box of a slice of an int, we only consider the struct for finding what impl blocks to consider their methods from. So that's why we only pass it in ADT, because we only pass in the ADT of the struct that's outside of the expression. And then for every one of those, we just we call basically something that considers whether or not that impl has anything useful. And all that does, we look through all the items in the impl. We look through all the items in the impl. We check if we are in the dot method call type of probe, not a path method call, but a dot method call. We need to make sure that that method that we're calling actually has a self receiver. We don't consider things that don't have a self receiver for a dot method call, but we do record it for later for diagnostics purposes. So if we try to call like a static function with the dot operator, we want to save that for later. Say that we saw it, we ignored it. We want to like maybe recall it later for diagnostics, and then we do some type logic to instantiate the self type of that method call, and we save it for later. We normalize it because we have associated types, and anytime we have associated types in the type system, we need to call normalize, and we push that as a candidate of something that we might want to consider for later, as this impl does define a method that has the right name and it has a self receiver, so it might be able to work, but we don't want to do any more work yet. We're not going to try to equate the type that we have against the self receiver of the impl method yet. We're just kind of stashing them, assembling all of them up front, stashing them for later, and then we'll use special rules to basically like winnow down the things that we're going to consider. So all this does is it just gets the item or the items that match the name that we're considering in this probe, and save them for later. So that, let's go back up the stack, and so back. So as I said before, inherent methods are things that don't have, like they're not methods for traits, except we have two special rules. So for object types like din traits trait methods for the thing that it's a din trait for, those are considered to be inherent methods of the impl. So when you have a din, like a din debug, you don't have to have the trait debug imported with a use statement to be able to call din debug. So you can call like, foo with a, x din std funct debug. So this std funct debug is not imported here. So if this was a regular type, we wouldn't be able to call x.fmt. This would basically say, I don't know what FMT function you're calling. I don't have any traits in scope that provide this method, except for din traits. This FMT functions are considered to be inherent, and this is just to make it easier to call din traits. So we also have to assemble some inherent candidates for object types, and all that does is it considers all the trait bounds on the din trait, and it looks on those traits to find methods that may satisfy what the method that we're looking for. And then we do basically the same process for parameter types as well. So let me slightly modify this example. So if we have some fun foo or t implements std funct display, we have t, then t.fmt also doesn't require std.fmt display to be imported with a use statement. We're able to just call it with a regular call. And this is for the same reason. We prefer I'm pretty sure. I hope I'm not lying to y'all. And if any of y'all know any better, then please speak up. But this is basically because we prefer methods that come from these super trait bounds over any method. Like basically, we have some if we have some like, trait, my own display that defines some method call, then we don't want to consider my own display trait over std fmt display just because std fmt display is not imported. We want to prefer the things that we've defined the bounds on this type T, just because in general, we don't know anything about this type T except for the things that we define, like the things that we say are its bounds. So that's why we give it special precedence. So other than that, I'm pretty sure we don't have any other special rules. We just have dynamic, which is object types, din trait, and then param as special rules. So yeah, that's that. What else? So that is assemble probe, which is calls from assemble inherent candidates. Once we've assembled all the inherent candidates, and as I said before, all we're doing is we're just accumulating all of these into a list stored inside the probe context. So we start out with an empty list of inherent candidates and then an empty list of extension candidates. We just want to populate these lists with as many things that we consider to be valid candidates that we could do method calls on. Later on, we'll pare down this list, given all the precedence rules and auto-deref rules that we have in Rust, but we specifically only want to consider these, or we want to consider everything first up front. So let's go do the same thing for extension candidates. So assemble extension candidates for traits in scope, basically, as I said before, considers the in-scope traits given the expression that we have. So given the expression we have, we look at its module. During name resolution, we also recorded all the traits that we imported using use statements. So we have a nice query that will give us back basically a list of all these traits that we want to consider. If we have those, then for each trait, we want to assemble extension candidates, which basically just does the same thing. I'm going to skip over trait aliases because they're weird. But basically, if the trait defines an item that matches the name that we're looking for, and it has a self receiver, if we're doing a dot method call, then we want to push a candidate for it. So basically the same thing, except for traits. All right, so that's that. Let's hop back up the call stack. And that is, that's basically the probe part of the probe. So basically at this point, we've created this thing called the probe context. We've assembled all the candidates that we're considering for this method that we're looking for. And we haven't done any winnowing. We haven't done any compatibility checking. We haven't done any checking the trait bounds match or anything like that. All we do, we have is this probe context that is basically locked and loaded, ready to go. And then we call this operation that we pass in, to probe up. In this case, we jump into the next step called pick. We take this probe context that we've just now populated with all of our candidates and we call pick on it. Are there any questions yet? No? Okay. Okay, so let's jump into pick. So picking is the next step. It's basically, that's when we choose the best candidate for us to do a method call, given all the interesting rules that Rust implements for preferring these methods over these, preferring inherent methods over built-in or over extension methods and things like that. So what we do is we, inside a pick, as this comment says, it's the actual search. We call this function called pickcore, and pickcore implements all of the logic. Instead of pickcore, there's pick all method. And instead of pick all method, this is the step that basically implements auto deref and auto ref. So we take these steps and recall that these steps are basically the auto-deref steps that we've assembled, this ladder of auto-deref steps, including these special unsize array to slice step. And we iterate over all these steps. We want to filter out the things that reference errors and the things that are unsafe derefs. Doesn't really matter why, because we don't usually care about that. And then we do a flat map over basically the 3 different. So for every auto deref step, we do the 3 autoref steps for every auto deref step. So if y'all are familiar with how autoref works in Rust, we basically try auto derefing our type, then we autoref once into a immutable reference, we autoref once into a mutable reference, and then if we consider const pointer methods, we try to turn a const mute like a const pointer to mute pointer, or a mute pointer to a const pointer, but I'll skip over that step. So for each one of these steps, basically the raw type, the type where we take a ref onto it, and the type where we take a mutable ref onto it, we call pick by value method. Pick by value method is basically we're getting into the kind of the more scrutinizing part of picking, where we make sure that the self type is actually compatible with the method we're calling. We do this by calling pick method. Inside of pick method, we consider inherent methods over extension methods. So basically inherent methods over trait methods. We do this in a for loop just to deduplicate the code, I guess. And we call consider candidates. So consider candidates is the step where we actually look at the candidate more deeply. We make sure that it's actually something we're allowed to call method on. As I said before, when we're considering like a struct, when we're considering struct candidates, we don't actually go deeper than one layer when considering the actual compatibility of the method and the thing that we're calling it on. So for example, if we have some struct wrapper t that just wraps a t, we implement a method on wrapper of i32, takes the self receiver, and then main let x is a wrapper of unit. So this does not, we can't equate this with wrapper of i32. We consider x.foo. During that initial method probe, we actually assemble this foo candidate as part of like assembled candidates is like wrapper of i32 colon foo, because all we do is we look at whether the outermost struct ADT step ID are compatible. Now we need to obviously filter that out now that we're considering candidates more seriously, and the way that we do this is with consider candidates. So we pass in that self type again, we pass in all the candidates that we are considering. So this is just an iterator over these candidates that we assembled during the first probe part. And for every candidate, we call consider probe on the candidate that we are going through. There's lots of layers of this method, but they all kind of don't do anything. In this case, we actually do we consider the receiver type of the thing that we're calling against the self type that we have. So inside of a probe, so as I said before, we don't want to have any side effects just yet. We don't want to take wrapper of underscore, and while we're considering whether or not what wrapper of i32 is foo, we don't want to like permanently infer that this inference type is actually like i32 just yet, because later on, if we're considering other candidates, then they would be automatically disqualified because we've already inferred this to be equal to i32. So we do this inside of a probe, so we don't have any side effects from inference. We don't want to define any opaque types. We don't want to do any opaque type inference. It's a simple trait inference. And we just try to super type. We do a super type relationship between the self type that we assembled during this probe, which is called X-form self type, and the self type that we have. the fact that this is a super type doesn't really matter, because during type checking, super type and subtyping only really matters for like region lifetime inference. So basically, just unless you want to get into the weeds of the way that we do the differences between subtyping and equation are, you can just think of this as we're trying to smush the two types together, make sure that all the types are equivalent. If this works, then we pass back all the things that we need to additionally prove, all the obligations that we got out of equating these two types. And we consider those obligations somewhere. So I guess I'm getting ahead of myself. So if this is true, then we continue on. If this is if this failed, then this probe result did not match. This type did not match. So no longer consider it to be a candidate that we could actually call. In this case, if we had wrapper of units, unit does not equal wrapper of unit does not equal wrapper of I32 because unit does not equal I32. So therefore, this would fail. We would basically disqualify this method from consideration and continue on with the other candidates we've assembled. In the case that it does succeed, we then want to do some additional checking on this additional checking. We want to basically do like a first pass check of the where clauses on the method. This is just because if a where clause is known to not hold on the self tie that we're trying to kind of call it on the receiver that we're trying to call it on, then there's no use to basically consider this method as something we could call it on. This is to help with ambiguity. So if we have a method that we know that could never be called because the where clause is never possible to call it on, and a method that we know that we can call because it has no additional obligations that we need to prove on it, we want to disqualify the one that we know is never going to be able to be called, so that we don't have an ambiguity between these two methods, because one is obviously the only one that we can call, because the other one is impossible to call because it has where clauses that aren't possible to be satisfied. So that's a bit of a roundabout way of saying that where clauses end up factoring in at this point. So the way that we get that is by instantiating the where clauses on the impl block that we have, the impl block that we're considering this candidate from, and we normalize these predicates. We get them from the wilds. We always have to normalize things that we get from the wilds. Anytime you call self.tcx and you get something back from it, you should probably normalize it for now. And we want to chain all the obligations that we get from normalizing and all the obligations we get from equating the types. And we just want to make sure that all of those may hold. They don't have to hold unambiguously, but they have to at least not turn into an error. They can be ambiguous because we might not have enough inference information to prove that they hold, but they should at least not error. And if they error, we set our result to be no match. We don't match anymore, and we basically just return from that. For trait candidates, we want to make sure the where clauses on the trait hold as well. Pretty sure that's how it works. Oh, actually, we want to make sure that the where clauses on the impl block that satisfies the trait that we're calling is satisfied. And if anyone wants to go into kind of more detail why we do that specifically, let me know. But basically, it's just like we want to make sure the where clauses for the thing that we're actually trying to call the method on hold. All right. So now we have basically disqualified all the obligations that all the candidates that we can not even possibly call at this point. Then we do one more. Oh, I guess we do consider the return type when it comes to method confirmation. So if we have a match and we pass in a return type as an expectation, so we say like, okay, we know that this method needs to return something that has this return type, then we also just want to make sure that the return type of the method is able to be subtyped against the thing that we actually have from the method. So this also just allows us to disqualify more candidates and have even less ambiguity. The more candidates we disqualify at this step, the less ambiguity we have, because the fewer candidates we have to consider, and the better error message we have. So yes, that is consider probe. So this is a pretty big function. It's doing a lot of stuff. It's doing a lot of type stuff. Any questions? Cool. So again, this is just best effort. We're not actually proving that the where clauses definitely hold. We're just making sure that we know that the methods that we are considering after this step don't have any where clauses that we know definitely don't hold. So it has no impossible to satisfy where clauses. And this happens inside of a probe. So that means none of this actual type equation is doing anything to inference yet. This is just kind of a best effort filtering that we do when considering candidates for the future steps of method calls. So jump back up to consider candidates, jump back up into pick method, not with unstable, pick method. And again, we're in a few different layers of functions here. One is that we consider basically auto deref from the top to the bottom. We want to consider things in the order that they auto deref. Inside of that, then we want to consider both first the type that we've auto deref to, then we want to take a immutable reference to it, look at methods that match that, take a mutable reference, look at methods that match that. And then for each one of those, we want to consider inherit methods first, and then extension methods, which are trait methods afterwards. So that's kind of gives a vague hierarchy of the way that we, like the order that we consider methods, and possibly why you've had strange occurrences where it's like, why did I call this method and it gave me back the return type that I didn't want? For example, why did I call clone on a reference to T and it cloned for me a reference to T? Because references implement clone when I actually wanted a T back. It's because even though we consider the return type, if T doesn't implement the type if T doesn't implement clone, then we give precedence over the thing that came before it in auto deref. That's a bit of a tangent, probably considers a little bit more nuance, but oh well. Anyways, so back up the method call chain. Where are we coming from? Yes. Okay, so we're back at pick all method at the top of our auto deref. Kind of hierarchy. At this point, we should have returned one method back that basically the first method in this big old hierarchy of considering all these different methods and all these different auto deref kinds and all these different auto ref kinds and inherent whatever methods. We have one method that passed the vibe check and basically is allowed to, that passes all the where clauses, matches the self type that we're looking for, and we pass it back as a pick result. Pick result is basically just a pick, which is the associated item that we're considering, and some information about how we got there, like do we have to auto deref, how many derefs we did, what's the self type that we got back. Let me jump back into my probe. So if that, sorry, I closed out the wrong file. Move up, called pick. So that's what we get back from pickcore. So basically, if pickcore returns something back, then we consider it. We return it back as our pick result. Returns none. Why does it ever return none? I guess if it returns none, that means that we got to the end of this iterator without finding a method that satisfies, and we do some additional consideration. So basically, if this pick fails, then we do some additional consideration. We consider those static candidates, as I said before. If you try to call a static candidate with the dot operator, then we want to consider those so we can give a nice method or a nice suggestion of use universal function call syntax to call this method instead. We want to consider the things that are private, things that we don't have within our scoping properly. And we also want to consider things that didn't completely pass all the where clauses. So we then can say this method can't be called because this where clause wasn't satisfied. So the rest of this is just diagnostics code. We look for methods that have similar names using left candidate. We assemble all the candidates, considering not considering things that are imported, all that other lovely stuff. But so once our pick is returned, we then get back our result from probe for name. That is here. I need to find the right caller for this. No, this one. Yes. So no, that's not the right function call. Yes, here. So lookup method succeeded. So lookup method's the thing that calls lookup probe. We get that pick back, as I said before. Once we have that pick back, we basically have one unambiguous method that we know what we're going to call. Now we need to actually do all that inference that we're talking about. And this happens here in confirm method. So confirm method instantiates. So we had the probe context, and that's what we're using to kind of assemble all the candidates and look at all the, all the things that we could possibly call methods on. We now instantiate this thing called the confirm context, which then also, because that's a bunch of methods, it just stores a bunch of common parameters that would be passing around to every single method. We kind of store those into the self type, so we don't have to pass them around. And we call confirm. So unadjusted self tie is the self tie that we when we called the check expr on the receiver, we got that. We need to now adjust that self tie properly, considering derefs, that array to the array to slice coercion, and then any auto refing that we have. So that happens inside of just tie. All we do is we look at the thing that all this information is passed back to us in the pick. So the pick tells us whether or not we need to do auto ref. Pick will tell us if we need to change like a mutable pointer into a const pointer for that call. Not super important to method calling, I guess, specifically. But now we actually do the real type checking, where we actually really check all the where clauses and actually really equate the self type against the thing that against the method's receiver. So we do this first by creating some fresh receiver substitutions. So that is the substitutions for the thing that we're calling it. So basically, if we have an inherent method, an inherent method on a nipple block, we need to create inference variables for all those for all the generics of the input block, and also for the method, I'm pretty sure it creates both for. Actually, it just creates substitutions just for the input block, so it doesn't create doesn't create substitutions for the generics on the method yet. Oh, it says it right here. The substitution doesn't include any parameters declared in the method yet. And this is just because we don't. The self type of a method doesn't reference any of the what is it? Any of the generics on the method. Sorry, I've been talking quite a lot. So first and then I guess right after that, we create the method substitutions using those parent substitutions and the method, the pick that we got in the segment that basically the name of the method and the pick that we got. We create the method substitutions basically same thing. We call astconv to make sure that we're actually calling the method with the right number of generics. We instantiate all of the, basically because you can, using the turbofish syntax, you can do like x.method, turbofish, like AB. It would be incorrect to create fresh inference variables for these two. We want to actually set them to A and B. So we call astconv, which is the thing that turns here, which is the almost AST representation of Rust, into the type checking layer of Rust. And we basically, if we provide generics using the turbofish, we turn these into their concrete types. If not, then we create some fresh substitutions for the generics that we didn't provide. All right. Now that we have the substitutions that we can use to plug into the generics of the trait or impl block that provides the method and the method itself, we instantiate the method signature using those substitutions. We get the signature of the method, which is like the input types and the output types and the calling convention and all that stuff. We also get all the where clauses passed back as method predicates. We'll have to use this later because we need to actually check them. So we'll register those as things that we need to prove later. And we do some weird stuff with substitutions here, but it only has to do with for diagnostics. But we take the signature, we get the self type of the signature, we normalize it. As I said before, whenever we call something, we get something from either TCX or from astconv, we need to normalize it because it might have some associated types with it. So we normalize it. We then unify the receivers. So we equate the self type against the method signature's self type. And this causes us to do, this has side effects. This will cause us to actually infer things about the inherent method that we're calling. So for example, if we have like impl, we have our struct wrapper, impl t, wrapper of t, defense self, or whatever, info. Then if we call that on a, x is a wrapper of unit, x dot foo, we equate x against, basically, we start out with our fresh substitutions as just inference variable, because there's only one generic on this method. We equate what our impl thinks that we have, which is a wrapper of, and I'm not going to care about lifetimes, but a wrapper of this, we equate this against what we know we have, which is a wrapper of unit. That causes us to infer that the inference variable in that impl block is actually unit. So that happens because we need to do it somewhere. So we do it here. We unify the receivers. I'm not sure if this actually has any interesting special logic. Nope, it's very simple. So we just equate them and register the predicates. So when we equate things, it might have some side effects. Like if we equate two consts, we have to register the fact that we have to prove later that those consts are equal to each other. Things like that. Let's see, let's jump back up. We normalize the rest of the signature now and all the predicates that we get. We have special logic. I'm not sure why it lives here. We want to make sure no one calls .drop, the .drop method, because it's illegal to be called. This probably could live somewhere else, but whatever. And is that all? Actually, where do we register this method predicates? We register right here. So now we have the where clauses on the method. We add those obligations here. So we basically register the where clauses on the method that we now have to check. Now that we have basically committed to calling this method, we now need to prove all the where clauses on it actually hold. We do it inside this method because we want to give it a obligation cause code, which basically explains why this obligation, why this predicate is required to be proven. We want to give it an obligation cause code that points back at the method, so we can give lovely method or lovely errors like where we point at an argument when t isn't sized and things like that. And this is done using an expert binding obligation, which basically points at the def ID and the call expression and the span of the call and things like that. All right, so now all that's done, we pass back a confirm result, which has a method callee in it. A method callee is much simpler now. We don't have as much information we pass back because we don't need to do much else after this. At this point, since we've chosen a method to call, all we do is we kind of just call it like a regular function call. So we still need to make sure all the arguments are compatible with the method. But that's common logic that's shared between function calls and function pointer calls and method calls and things like that. So all we need to do is pass back the method that we're actually calling, the generics of that method and the signature of the method. We pass back the signature of the method because we've already computed it. We could compute it again by calling tcx.fnsig, which is a query that gives you the signature for a def ID, pass in this def ID, put in the substitution. So, but then we would have to normalize it again. It's a lot of work. So we just pass the signature back. And yeah, so that's confirm. So once we've confirmed the method, no, I jump into the wrong method again. It's here. Once we've confirmed the method, we have some extra bookkeeping for whether or not we had an illegal sized bound. This is purely for diagnostics. I'm not really going to go into it because it's kind of funky. What we do is we pass this method callee thing that we just constructed back up to the caller. We record that this expression ended up, resolving to this method, so we can use that later. So later on, in later steps like mirror building, we need to know what method we actually ended up calling, because we don't want to have to repeat these steps over again. So we record what method we actually ended up calling here, and we end up returning this method. Or we bubble up this method one more time, and then we call check method argument types, which just calls check argument types. This checks that all the arguments you pass to the method are actually compatible with the method, and does all the inference and provides a bunch of type errors, and does all the lovely, you like specified BA, flip them to call AB, does this complicated kind of satisfiability matrix algorithm to do that, to provide really nice errors. Okay, well, I'm sorry, Waffle. I totally jumped over your errors or your question. I'm assuming this is back in when we were doing the consider part. I guess to answer your questions, how do we decide that a predicate may possibly hold? We use a trait solver. So the inference context has a method called predicate may hold on it, and you give it a predicate, and it will tell you whether it holds. Returns this thing called an evaluation result. So it's an enum called evaluation results. And it either says, yes, it was successful, but it possibly needs extra borrow checking. It's ambiguous. We don't know whether or not it holds, or it is an error, or it's recursive. And the details of how that actually gets proven is a little out of scope for this. But basically, method probing doesn't really care. It just calls predicate may hold and uses the result. All right, any more questions? Any questions about method calls? No? All right, well, exercises. Right, so that is method calling. At the end of the day, I don't want to say it's simple, but it's pretty straightforward logic. A lot of the complication, a lot of the stuff I skipped over was diagnostics code, features like like custom self type receivers, and other things like that. That at the end of the day, we basically just iterate over all the options of methods that we're allowed to consider. We assemble them all up into one big bag, and then we do auto dereffing and auto refing, and then inherent and extension consideration, basically inherent impulse and inherent impulse and like trade impulse, and we consider all those kind of in order until we find a method that does satisfy all the things that we want, or could satisfy all the things we want. As I said before, we don't need to prove all the where clauses do hold. We just want to prove that they don't not hold. Once we have the pick back from that, we confirm it by actually equating all the types, instantiating all the where clauses, registering those where clauses, and returning the method function signature back. And peppered in through all that is a lot of diagnostics code and other things like that. But anyways, it's pretty straightforward. Other than that, it's just quite a lot of code, quite a lot of kind of considerations. If you didn't know that we wanted to support calling len on an array using the slice len function, then it might be confusing why we assemble that extra candidate or extra method auto deref step. So that's why. And if you didn't know that we wanted to disqualify some functions that are known to be impossible to hold, like where its where clauses are impossible to hold, then it might be confusing why we enter into a probe like 4 different times to do kind of what looks like identical work. And if you didn't know that we had a very specific order that is kind of backwards, like it's like a backwards incompatibility hazard of the orderings of the way that we consider both inherent versus extension methods, and also the order that we do auto dereffing and refing, then it might be complicated to understand why we do everything the way that we do it. But I hope that I illuminated a little bit of that over the last hour and 15 minutes. Any questions? Any last questions? Otherwise, we might want to just call it. Anyways, that was kind of a whirlwind. I jumped over a lot of steps. I don't think I achieved either kind of a high level versus a low level walk over this code. So if you have any questions, you know where to reach me. File a bug and tag me in it. Don't actually file a bug and tag me in it. Just message me on Zulip or on Discord or on, I don't know. Zulip is probably best. And yes, Matthias said, yes, let's call it. Now that we know how to call things. Anyways, thanks for joining. This will probably be uploaded onto YouTube. So YouTubers, if you all have any questions, please let me know, pick my brain. Now that I've kind of gone over the high level stuff, I'm very welcome to, or y'all are welcome to kind of pick the specifics out. The reason I wanted to do this was mostly just because I didn't want to have to explain all these high level steps, especially like the kind of conceptual problems of why we do method probing the way that we do it. But I'm more than welcome, or y'all are more than welcome to ask questions about the specifics of why does this method do this, or this looks weird, or like why do we use an iterator here? Why do we clone this thing? Why do we use canonicalization here? Things like that. Because I did skip over quite a lot of the steps that kind of make things. I skipped over the things that were like optimizations and things like that. So there's a lot of fun little interesting things, and method calls are very important to Rust. So a lot of this is load bearing in interesting ways. But I could probably answer your questions if you have them. Anyways, okay. All right. Well, thanks for joining. That's it.